Hello everyone. In this video, we are going to look at Lagrangian formulation of rigid body kinetics. I know that under playlist dynamics, I have referred to this topic in brief, but here I'm going to talk about this formulation in more details, especially since we are going to use it to formulate the equations of motion for robots. So in Lagrangian formulation, the variables that we choose to describe the configuration of the system, we call them generalized coordinates. And these generalized coordinates are the same as what we had before. Like, for example, if you have a pendulum, for example, a vertical pendulum, then the deviation angle from the vertical position theta might be what you consider for describing the configuration of the pendulum, but that's not the only choice. Another choice you can have is x and y coordinate of that pendulum bob, as you can see here. Now, the most important thing about these generalized coordinates or Q's is we try to choose the most convenient set of parameters. And the other thing is the number of independent generalized coordinate is the same as degree of freedom for the system. So for example, for this pendulum, what we have, the degree of freedom is only 1. So ideally, we better only go with one generalized coordinate, which in this case is theta, and that works just perfectly. But if we go with this configuration, as I said, this selection of x and y, here we have two parameters, two variables in my generalized coordinate vector. So since the degree of freedom is one, that basically telling us that there is something called a constraint, right? And here the constraint is, of course, the length of the pendulum is constant, L. So now we'll drive the equation of motion for the pendulum both using x, y, and theta, and you'll see that if I can choose those generalized coordinates to be independent from each other without any constraint, that is definitely the most convenient set of parameters, okay? Because incorporating constraints into the equations of motion or Euler-Lagrange equations needs some further calculations. And one other thing about convenient is when you have these external forces or couples, like here, this torque applied at pinpoint O, what's the easiest set of parameters or parameter that is related to the work of that force or couple? So here, the work done by T in general, if T is constant, is going to be T times delta theta, if T's variable is integral of T d theta. And you clearly see naturally that torque, the work of that torque is described using the change in the angle, not the change in position x and y. So if I want to find what we call later, you'll see what we call the generalized force, or QI, for that specific what we call generalized coordinate. It's better that these forces and couples, external forces and couples, the work of them is described using those generalized coordinates, not something else. Clearly, as I said, in this case, the work of that T is described using theta, not x and y. And if it's described using x and y, then finding the generalized force for x or for y, as we'll see, needs some further calculations and mathematical operations. So we'll get into more discussion of what do I mean by most convenient. The first time derivatives of these generalized coordinates is what we call generalized velocity. So if we show generalized coordinates by Q or Qi, then Qi dot is what we call a generalized velocity. And finally, there is one more term called generalized momentum or momenta, which is as you will see, is the partial derivative of the term called Lagrangian L with respect to that specific q dot. So before I can describe that, I need to talk about the Lagrangian. So what is Lagrangian? Because this method, as you clearly see, is called Lagrangian formulation. So in here, we need to form a term called Lagrangian. What is Lagrangian? It is defined as the difference between kinetic and potential energy. So K is the kinetic energy of the whole system, and P is the potential energy of the whole system. If your system is only comprised of rigid bodies, you know, in a rigid body you have two terms for kinetic energy: a translational term, which is half of the mass velocity at the centroid squared, plus a rotational term, which is half of mass moment of inertia about centroid times rotational velocity squared. Okay, so that's kinetic energy. And again, if you have a system, you have to add all of those terms together. Potential energy, in most of the mechanical systems, it is coming from gravity and spring forces, right? If you have an electromagnetic system, then it can come from electric and magnetic potential energies. But here, where most of our robotics problems, we barely even use springs too. So most of the time, this potential energy is only due to gravity. And one important assumption that we make in driving the Lagrangian equations is that potential energy is not a function of velocities. It's only a function of position or generalized coordinates. So partial of potential energy with respect to the generalized velocities is zero, right? And you know, for gravity is definitely a function of vertical position, right? So any other type, even for spring, it is still a function of the deflection. So definitely in this formulation, we always have this assumption. Whenever this assumption for any reason violated the Lagrange-Euler equation, which is what we use to drive equations of motion, this will not be valid. Okay, so we have to keep in mind the assumption that we have. Now that I know what is Lagrangian here, and I know the generalized velocity q dot, the partial of Lagrangian with respect to q dot, I call it what? I call it generalized momenta. Okay, and if this q dot is a vector, which in most of the time it is, because you have more than one variable, then this momentum here is also going to be what? A vector. And this is almost the same as what we had in the past. It's just a new basically formula, but the same concept, because if you remember, if I only have a single particle, let's say, right, and this guy is moving with a velocity x dot, correct? So position of it is x, velocity is x dot, and this is mass. You clearly know that the kinetic energy for this is 1/2 m x dot squared, and potential energy of it, P, is no function of x dot. So in this case, your L, the Lagrangian, is going to be 1/2 m x dot squared minus P, which is only a function of x, not x dot. So here, if I take partial of Lagrangian with respect to x dot, what is it? Clearly, it's only going to be m times x dot, and m times x dot is exactly what in the past you used to call what? The linear momentum P. So you see, that's the same thing. By the way, here I want to emphasize a couple of things here, so you're not confused. There are two P's here. One is a small p, the other one is large P. This P here is a scalar, that's potential energy. This P that has the vector, that's the momentum, and it's in small case, not capital letter. So these two P's are two different things. If it's not convenient, you can call this P something else. But just keep that in mind. Good. So now, with that definition of Lagrangian, with this important assumption, now the Euler-Lagrange equation of motion can be written as time derivative of partial of L, or Lagrangian, with respect to q dot minus partial of L with respect to q is equal to what? Equal to qj, where qj, as I said, is called generalized force, associated with the generalized coordinate qj. Okay, and the derivation of that is, if you want, I can derive it in a separate video. In this video, my goal is not to derive it, but what you really need to do is to use the principle of virtual work and the D'Alembert's principle. If you apply those, then you can show that if you use the variational approach to minimize this cost function integral of L dt. Okay, so the goal is this. If I want to minimize this integral of L dt, where L is a function of q, q dot, and t. If I want to minimize this, correct, then the function q of t, which allows this integral to minimize, so basically the argument of minimum of this thing, the solution of that will be q of t. If you call it q of t, then q of t would definitely will be plugged into this equation, and the equality will hold. Right? So again, if I want to use the variational approach to minimize this integral of Lagrangian versus time from t1 to t2, t1 and t2 are the time over which the motion is happening, then for that to happen, I need this basically set of differential equations to be valid. And this integral here, the integral of Lagrangian versus time, is called the action integral. So the actual solution is the function that minimizes the action integral, and this is basically how the nature works. When it moves from one point to another, the configuration of the system, the degrees of freedom of the system, choose those paths, chose those functionalities that minimizes this integral. Okay, principle of least action is another way that we can describe this. So this is, as I said, these are the set of differential equations or the equations of motions that you will get. We call them Euler-Lagrange equations. Derivation of that, if you want, I can do it in a separate video to save on the time. And here I'm going to apply this to several examples. I'm going to apply it to the pendulum, apply it to the mass spring system, apply it to a robot with a basically one single link. I'm going to apply it to systems with more than 1 degree of freedom. I'm going to apply it in systems with holonomic and non-holonomic constraint, and so on and so forth. Okay, so we are going to solve a bunch of examples and see how to apply this Euler-Lagrange equation to different systems with different degrees of complexity. So let's start with some very simple cases, the mass spring system and the pendulum. And here we can add to the complexity of the mass spring problem by adding a damper to the system and adding some friction, right? So here is the viscous damping with coefficient B, and we can add some Coulombic friction here too. Plus some external force F. So first, let's do the pendulum example. And so if you notice for the pendulum, we can select different parameters as our generalized coordinates. The simplest case is the angle theta. And here the kinetic energy of the system K is 1/2 mass times velocity of this object squared. And since this bob is rotating about point O on a constant radius of L, then definitely it is a circular motion, and in a circular motion about a fixed point V, as you know, is equal to radial distance, which in this case is L times omega, and omega means theta dot. So magnitude of V is L times theta dot. So when we say 1/2 mv squared, it's like 1/2 m times L theta dot, the whole thing squared. Potential energy, you measure it from a datum, and in this case, I'm going to consider the lowest point of the pendulum, like the pedigree, basically, you can call it. This point here to be my datum of potential energy. And if that is the lowest potential energy of 0, then when you change the angle from 0 to some theta, the center of the pendulum is lifted by this distance delta y, which, as you know from simple geometry, this is L times L minus L cosine theta. And so the potential energy P is going to be mg times delta y. So it is going to be mg, and if you factor out L here, it's going to be L times 1 minus cosine theta. And that's it. So if I want to continue here on the right side, the Lagrangian L is K minus P. So it is going to be 1/2 mL squared theta dot squared, and then minus mgl times 1 minus cosine theta. And now if I apply my Euler-Lagrange equation with the only q that I have to be theta, then you will get what? So here I calculate first my partial derivatives that I need. One of them is partial of this Lagrangian with respect to the theta. The other one is partial of this guy with respect to theta dot. And partial of it with respect to theta, clearly you see it's the only term you have is positive mgl cosine theta. So it's going to be negative mgl sine theta. And this one is definitely going to be ml squared theta dot. Now time derivative of this minus that is going to be equal to generalized force for theta dot. So this is my Euler-Lagrange equation. Q of theta, and here this Q, as I said, is those non-conservative forces. This is not all of the forces acting on the object, because the conservative portion of the forces acting on the object is already considered into this potential energy term here, right? So since you are calculating potential energy, you are indirectly bringing in the forces done by conservative forces. So this really is a non-conservative force. And if you look at this pendulum here, at any point, if you draw the pendulum or the whole system really, on the system there are three forces acting. If you consider it as a system, then there are two forces really, right? There is the torque and there is mg. Mg, as I said, is already considered in potential energy. So the only thing left is torque. And the work done by the torque is what? If you look at the small work done, virtual work done by torque, the virtual work done by this torque is going to be T times virtual displacement delta theta. And in this system, the only, as I said, generalized coordinate that I have is theta, so you can say this is equal to Q of theta times delta theta. And from here, clearly your Q of theta is equal to the torque. Right? So we always use equality of the virtual work done by actual couples and forces and set it equal to the virtual work done by these generalized forces, and then through that equality we find what are those generalized forces or moments going to be. So if I use what I have here, it's going to be the time derivative of ml squared theta dot, so it's going to be ml squared theta double dot, the first term, and minus a partial derivative of L with respect to theta, so minus this term, so it's going to be positive mgl sine theta. This is equal to the torque. And guess what? This is exactly the equation that you will get from applying the Newton method, right? If you apply the sum of the moments about the pivot point, point O here, right? If you apply sum of the moments about this point O and say sum of the moments about point O is equal to I about point O times alpha, which is what you had in Newton-Euler equations, sum of the moments here about point O is clearly T, and then it is going to be negative mgl sine theta, the moment of mgl, mg, right? This is L, this is theta. And I about O, since it's a basically discrete mass, a point mass with mass m, distance L, I about O is going to be ml squared, based on the definition of mass moment of inertia. And you know alpha is the angular acceleration, which is theta double dot. So this equation that you will get from Euler-Newton equations is exactly what you get from the Lagrangian formulation. So you see the answer is the same, right? So this is the simplest example you probably can solve, the pendulum. Now, as I said, I want to raise the bar a little bit and add some more forces, and then we make it harder and harder, or more involved really, not harder. So here again, your system has 1 degree of freedom x, and the forces applied to the object are external force F, the Coulombic friction, which we can say it is basically the constant mu k, right, times n, where n is the normal force. We have the force of damper Bx dot, and we have the force of a spring Kx, assuming that they are linear, acting linearly. Then in this case, if we want to look, your kinetic energy K is definitely 1/2 mass times velocity squared, and velocity is x dot. Your Q is going to be only this x. Potential energy due to gravity you don't have because the object is moving horizontally. There is no delta y. The only potential energy is here stored in the spring, so potential energy is going to be 1/2 k x squared. And from here, clearly your Lagrangian is going to be 1/2 mx dot squared minus 1/2 kx squared. And if you calculate those partial derivatives that you need, one of them is partial with respect to q, which is x here. It's going to be negative kx. The other one is with respect to x dot, which is going to be mx dot term. And now if we apply our Euler-Lagrange equation, d over dt of this term here, minus partial of L with respect to x is going to be q of x. And if we continue here, this is going to be the derivative of this term. It's going to be mx double dot, assuming that the mass is constant. This is going to be negative kx, so it's going to be positive kx. And the only question is now, what is this q of x, right? What are those non-conservative forces acting on the system? And if you look at this system here, if you look at this block with mass m, clearly at any point there are several forces acting on it. There is the external force F, there is the spring force Kx, which we included already. There is Bx dot, which is the damper force. There is the Coulombic friction, which is mu k times n. And there is n and mg. mg is not doing anything, n is normal to the direction of motion, has no work. So now from this FBD, free body diagram, we have to come up with what is this q of x. And clearly here, as I said, this one is already taken care of. These two don't do anything. They are perpendicular to the direction of motion. The only forces that are non-conservative and you have not considered are these guys. And it's not really hard to show that. It is going to be, of course, F with plus sign, and then these two forces with negative sign, mu kn and bx dot, which are opposite to the direction of motion, right? Because definitely the virtual work here done is going to be q of x times delta x, but in the real world it is negative kx, or negative k is already considered, negative bx dot, negative mu k times n, and you know n is the same as mg, right? So if you want, you can replace it with mg, and then positive external force F, this whole thing times the displacement delta x. So clearly your Qx is all of these forces, and we can plug them in. So it's going to be F minus Bx dot and then minus mu kmg. And this is exactly, again, the equation that you will get from sum of the forces equal mass times acceleration. Because if you take this term to the right hand side and make it negative kx, this is your mass times acceleration, and then all of that is going to be summation of the external forces in the x direction, right? F in the positive, spring, damper, and friction, Coulombic friction, all in the negative direction. So it is definitely giving you the same thing as before. Good. So far we dealt with simpler examples. So now let's look at, raise the bar a little bit, and take a look at the cases where there are constraints. Or you choose your vector for the generalized coordinates to be your inconvenient selection, and that kind of brings with it a constraint. Like what? Like the pendulum again, but this time instead of me choosing theta, I choose x and y, which definitely has a redundancy because I only have 1 degree of freedom, so I really need one of them. There is a constraint between x and y, which is the constant length of the rope. And the question is, if I have this one, can I still get my governing equation of motion using this Lagrangian method? And the answer is yes. How? So here, we divide our constraints into two categories, holonomic and non-holonomic. Holonomic means that the constraint is only described between the q values. So we can write it as a of q equals 0, where a is in general a nonlinear function. Could be linear too, but in general nonlinear. So again, the constraints are only written among the generalized coordinates. There is no generalized velocity. There is no q dot between them. Right? So you clearly see here it is written between x and y. There is no x dot or y dot term. And the other way to describe it is, if even they are written in terms of q dots, you can integrate it and convert it into what? Convert it into the equivalent equation that is only among q's. So you can eliminate q dots in that constraint equation, then we call it integrable or holonomic. Not every constraint that you see in real world in physical systems is integrable. Some constraints, like what we'll see later, like no slip conditions for a rolling disk, whether it's in 1D or 2D or whatever, they are not always integrable. You cannot always convert a constraint that is between the velocities into a constraint that is between the positions. And dealing with non-holonomic is a little bit different than dealing with holonomic constraints. So let's look at the holonomic constraints, the position constraints really, and see how we can deal with such scenario. So here, as I said, instead of me choosing what? Theta, I choose my q vector to be x and y. So here I choose 2 generalized coordinates instead of 1. Therefore, I have to use that Euler-Lagrange equation twice, one time for x, one time for y. Right? And then try to eliminate between them maybe and get it down to one equation, because ultimately I have 1 degree of freedom. That's one way to do it. The other way is, can I, from this constraint equation, eliminate one of the parameters in the beginning and be done with it? Can I eliminate that redundancy? Can I eliminate the constraint by finding one based on the other? Well, that's not always possible. Sometimes this function a of q, the nonlinear function, is complicated. It's not always easy to find one parameter as a function of the other. In this case, you can. In this case, if you want x, you say x is what? Plus or minus square root of L squared minus y squared. But not always finding such thing is possible. So let's take a look at both scenarios. We'll deal with this problem in 2 different ways. In one, we find x based on y and eliminate it. In the other one, we will not eliminate the constraint. We will not eliminate one parameter based on the others in the constraint and directly incorporate that. How? Let's find out. So first, let's say we can find and eliminate the redundant q. Now what? So in this case, if you remember, the Lagrangian is equal to k minus p, but here your k is the kinetic energy, which is 1/2 mv squared, and potential energy is going to be negative mg delta y, or positive mg delta y really. Remember, here we chose this very bottom point to be the datum of the potential energy. So let's look at these terms, v and delta y. V is the velocity of the particle. If the coordinate of the particle is given with x and y, then this v vector is going to have 2 components, x dot and y dot. So v squared is going to be what? X dot squared plus y dot squared. And what about negative mg delta y? So here I'm going to choose my x-axis to the right and y-axis to be upward. Then y of the datum, y of 1, is going to be negative L, and y of the 2 is just y, right? So this negative mg delta y is going to be y2 minus y1, which is basically y plus L. So that's my Lagrangian. Now what? Now, the problem here is if I want to write everything in terms of y, so here I'm trying to use that method of eliminating one of the variables. If I want to get rid of one of these variables, let's say x, because I have y and y dot in 2 places, x and x dot only in 1. So let's get rid of this x dot term. How? I try to use the constraint equation and get rid of x dot based on y dot. How? I take a time derivative. If I take a time derivative out of the constraint equation, that becomes 2x dot plus 2y dot equals 0. If I eliminate the 2's, now clearly from here, your x dot is going to be y dot with a negative sign over x. And if you square it, your x dot squared is going to be negative y dot squared over x squared. But remember that I need x dot squared. So it's going to be y squared, y dot squared over x squared. And what I do, I replace this x squared because I don't want to have any x or x dot. I replace this x squared from my constraint directly. So instead of doing x, I use x squared, right, which is L squared minus y squared. I plug this into that equation. If I do so, you will get y squared, y dot squared over L squared minus y squared. This is your x dot squared. So if you plug it down here, you will get 1/2 m times x dot squared plus y dot squared, and then minus mg times L plus y. Right? So as I said, you bring this guy and plug it right here. Now, can I do a little bit simplification here? Yes. If I take a common denominator here, then it's going to be L squared y dot squared minus y squared y dot squared, and that y squared y dot negative with this positive term would cancel out. So you will get L squared y dot squared over this guy. So this whole thing, if you simplify it, it's going to be L squared y dot squared over L squared minus y squared. Okay? So this is your Lagrangian. So let me write it down in a clear manner. ML squared over 2 y dot squared over L squared minus y squared. This minus mgl plus mgy, or minus mgy. Okay, so now this is in a lot nicer format. And now I'm going to calculate those partial derivatives, right? One of them is partial of Lagrangian with respect to y. The other one is partial of Lagrangian with respect to y dot. With respect to y, you have this term and this term. In here, it's a ratio. And the y dot term is considered like a constant, so you can get it out of the derivative, like this. And partial of this 1 over L squared minus y squared with respect to y is the derivative of numerator, which is 0 times denominator minus that negative 2y divided by denominator squared. So you get 2y over L squared minus y squared, the whole thing squared. And then this term has no y derivative. This term is going to be negative mg. And with respect to y dot, is simply going to be ml squared over 2 times L squared minus y squared. 2y dot, that 2 with this 2 would cancel out, and you will simply get this guy. So these are those partial derivatives that you need in your Euler-Lagrange equation. Moving forward, now partial of L with respect to y dot, when you take time derivative of that, minus partial of L with respect to y, this should be Q of y, right? So if I expand this, that should give me the equation of motion. So here I need to take time derivative of this guy here, but you know this one has 2 variable terms. So I have to pay attention to the taking derivative, add the negative of that term, and then figure out what Q of y is so I can get my equation of motion. Okay, for the time derivative. So it's going to be derivative of first one times second one. Again, this is a ratio. And since we are taking time derivative, the y dot term will show up because of applying the chain rule. So it's derivative of this one with respect to y times y dot, which is basically, it's going to be 2, the 2 would cancel, so you would get ml squared times y divided by the denominator squared times y dot, and there is another y dot here, so it's going to be y dot squared, and then plus first one times the derivative of the second one. So far this is just the time derivative minus partial of L with respect to y, which is already calculated. These two would cancel out, so you will get mL squared y dot squared divided by L squared minus y squared, the whole thing squared, and then plus mg is equal to. And the only term that I did not do correctly is this is going to be 2y over that. So there is a 2 here, or here actually. Yes. So there is a 2 here. Everything else looks correct. And now these two terms, as you clearly can see, they are the same term, this one and this one. Except this is 2, that is 1, so I can simplify one of that with this one. And the rest of them stay. Now, what about Q of y? As I said, you have to use the virtual work. The virtual work done on the system is by the torque on the pendulum, T delta theta. Okay. That's the thing that you have, correct? That's all you have. It's the only force that you did not consider, and this should be equal to Q of y delta y. And from here, you have to find Qy based on theta, or based on t. But since this is delta theta, this is delta y, you cannot set the two sides equal and find Qy based on t unless you relate y to theta. And for that, we need to use the geometry here. Remember that here y is, if you look at it, your y is clearly L times cosine theta with a negative sign. And if you take a variation from both sides, it's going to be delta y is equal to positive L sine theta variation theta. Okay? So if that's the case and you plug that in here, you will get that T variation theta is equal to Qy times L sine theta times variation theta. And if you consider simplification here, your Qy is going to be T over L sine theta. The problem here is I want all of my ODE, which I'm trying to get in here, to be a function of y, no theta in it. So I have to replace theta based on a function of y, right? Clearly, I have to relate theta to y, because L sine theta is clearly x, as you know, right? You clearly can see here that L sine theta is x. So it is basically here, this Q of y is like T over x. And x, if you remember, it was square root of L squared minus Y squared. If you consider here your X to be on the positive side, let's say. If it's on the negative side, then you have to use the negative square root. Correct? In general, it's like plus and minus. So now it is a function of Y and it can go here. And so now your final thing is going to be like, you see all of these terms have ml squared in them. So if you do that, it's going to be ml squared times, and they all have this L squared minus Y squared in them too, but if I want to keep it, it's going to be like this. And clearly you can see this ODE is not as basically simple. The derivation of that, the look of that is not comparable to what we had, which was this guy. Right? Absolutely, it changed the form of my differential equation. Compare these two together, and you'll feel that when you choose the wrong coordinate, when you choose the wrong generalized coordinate, it can change your differential equation, the governing equation of motion, to something that is much harder to derive, much harder to solve, and it's not going to behave so nicely, because here you have to decide in each motion whether you choose the positive side or the negative side. You have to keep track of that. Okay, so that's why we said choose the convenient ones. Choose the ones that, especially when you go to find those generalized forces or the kinetic energy or the potential energy. Here the potential energy was not bad in terms of Y. The kinetic energy was a little bit harder and the QY was much harder. Okay, so theta is definitely more convenient than Y is. So here was how you could deal with the extra Q that you chose, the redundant one, and how to deal with the holonomic constraint. If possible, I would like to find one of them from the constraint equation and eliminate it. Another example before I move forward to talk about the cases where you cannot, the equation of holonomic constraint is complicated, you cannot even do this elimination, is the example of a single link robotic arm. So here you have one single link robotic arm that is attached to a motor, driven by the motor, but through a gearbox. And here you have two variables, theta L and theta M. Theta M is the angle of rotation for the motor. And since in gearbox you have most of the time a reduction in the angular velocity, then the output of the gearbox, so this theta M is the input of the gearbox, the output of the gearbox, which is called theta L, that is typically much less than theta M, right? Or theta data that is less than theta data of M. And this amount of reduction in this angular velocity is called R, the gear ratio. So you can say theta M is R times theta L, or theta dot M is R times theta L, where again R is called the speed ratio or the gear ratio. And it's theta L that is the angular velocity of the robotic arm, really, not theta M, the rotation of the rotor of the DC motor. So here, again, you see I have two variables. And I can say, well, my Q is going to be basically my theta L and theta M. But instead, I just try to focus on one of them, in this case, theta L, which is the actual angle of the link, and try to relate this theta M to theta L through this equation and eliminate it. So in my kinetic energy, potential energy, or the generalized forces, I'm not really going to use both of them. Through my constraint equation, I'm going to eliminate this. Okay, and that way I can get my equations of the motion in a simple form. So first, what is kinetic energy? Kinetic energy is due to two parts. And both of them are rotary parts because all I have here is only showing a pure rotation. So it's the term in motor, right? 1/2 j of the motor times theta dot m of the motor plus 1/2 j of load times theta dot l of the load. And since theta dot m is r times theta dot l, I can replace it, right? Because all I need is to take a time derivative from this constraint equation, correct? And that means I can eliminate this theta dot m term as, when you square it, it's going to be r squared theta dot l squared. And if you factor out theta dot l, your equivalent, this is what we call J equivalent or J effective. J equivalent of the whole system is going to be J of the link plus R squared J of the M. And this is very important. Why? Because although the inertia of the motor shaft is much smaller than the moment of inertia of the link, about the same axis, the thing is, this gear ratio R is typically a large number, right? Because most of the time for many robotics applications, the motors are rotating very fast and we don't want a robot to move that fast. So we typically use a big reduction, typically, let's say 100 or so, and we bring down the RPM by a significant amount. So when the R here is squared, that is going to be a very large number. If R is 100, R squared is 10,000. So although J of the motor can be much less than J of the link in real life, when you multiply it by 10,000, now it can even dominate the J of L, right? And be much larger than that, or comparable if the link is quite heavy. So in this equivalent, J equivalent, you have two terms, not really one. Dominant one, which is JL. If there is a dominant, most of the time it's really the R squared JM term, which is becoming dominant. Unless your gear ratio is really small or your motor, you can really rotate it at a very small RPM without the gearbox. So that's your kinetic energy. The potential energy is definitely the potential energy of the link, because that's the only one that changes the Y of the centroid of it, right? Because the gear, the shaft of the gears and the motor, the centroid of them stays on the same place, but the centroid for the link does change its vertical position, and this change in this position due to change in angle theta L is what makes the potential energy. If you look at the potential energy, this is very similar to the pendulum, because it is a pendulum really here, and it is mgl times 1 minus cosine theta. So you see this is identical to what we had for the pendulum. So the derivation of that is just like what we had before. So the Lagrangian is the difference between them. And now, if you calculate your partial derivative terms, right? First of all, as you can see, everything is written in terms of theta dot L and theta L. There is no theta dot M or theta M anymore. So one is partial of this Lagrangian with respect to theta L, which is clearly only this term here. This is going to be positive mgl cosine theta L So the partial of that is going to be negative mgl sine of theta L. And the partial of this Lagrangian with respect to theta dot L is going to be, as you can see, j times theta dot L. Right? And then the time derivative of this, which is this term, minus the partial of L with respect to theta L, so minus this term, which is going to be plus mgl sine theta, this term. This is equal to the generalized force for theta L, right? So when I say d over dt of partial of L with respect to theta dot L minus partial of L with respect to theta L, and this is equal to the generalized force for theta L, then as I just explained to you, this term is j times theta double dot of L. This term is going to be positive mgl sine of theta L. And what is q of theta L? For that, I need to again use that variation approach. So the virtual work delta W in the system is equal to what? If you look at the real physical system, there is a torque generated at the motor, right? Which here it is shown by tau m. So tau m here is the torque generated on the motor shaft due to the applied voltage and electric current. We'll talk about this later in more detail, but if you just consider this to be the external couple applied to the gearbox input, that's one thing that you have external to the whole system, which is the motor, gearbox, and link. And the other thing that you have here is basically the viscous frictions. So there is a viscous friction here applied to the motor shaft, and there is a viscous friction applied to the load shaft. So here I show them by B of m times theta dot m, and by B of L times theta dot L, okay, to the input and output shafts of the gearbox, basically. And so we can find Q of theta L based on these three guys. So for that, as I said, we have to use the variational approach, and we can say the variation of the work done by these three, it is going to be theta m minus B of m times theta dot of m. This is applied to the delta theta of m, and then minus BL theta dot L applied to the theta L. And if we say this whole thing is equal to the generalized couple in this case, Q of theta L times variation of theta L, then I can find Q of theta L from here. All I need to do is replace this theta dot m by r times theta dot L, right? And the variation of delta theta m by r times variation delta theta L. And they both come really from the initial definition of theta m is r times theta L. Because if you take time derivative from it, you get the first relation that we used. And if you take a variation from it, then you will get the second one that we used. And here, if you simplify this delta theta L's on both sides, you will see that your Q of theta L, it is going to be R times tau m, and then you have basically minus PL theta dot L, and then here you have one R, here you have another R, so it's going to be R squared. So if you want, you can write it as minus PL plus R squared times BM, the whole thing, times theta dot L. Okay, and this is going to be your governing equation of motion for a single link robot if the torque from the motor is tau m, and here we neglect the electrical circuit and the voltage to that electric circuit that generates tau m. So input, we consider it tau m, not the input voltage to the motor. Okay, and if you remember, this J effective here was J of L plus R squared times J of M. If you remembered, this J of M, although small, is multiplied by this huge number R squared. And you see a similar effect here, that the viscous damping, viscous friction for the load is added to it, the one for the motor, but multiplied by R squared. So if you want, you can call this whole thing also be effective. And if that's the case, then my equation will be J effective times theta double dot of L. And if you take everything else to the other side, it's going to be R times tau m minus B effective, the damping term, times theta dot L, and then minus MGL sine theta, which is the term due to gravity. So this is another way to formulate the equation of motion for a single link robotic arm, considering the effect of the gearbox. So this is the end of the first video on Lagrangian method. In the next video, as I said, I'm going to show you how to find the equation of motion for the pendulum if we don't eliminate x and x dot from the terms and get down to two equations. And then we also will see how to incorporate in general, even if they are non-holonomic constraints or something, how to apply that and how to work with systems with more than 1 degree of freedom in general, whether they have a constraint or they don't. So hopefully this video was useful to you. I will see you in my second part of Lagrangian formulation of rigid body kinetics. Thank you.